Welcome to Prep for FE. Today, we master the exact mathematical distinction between pound force and pound mass as defined in the NCEES handbook. In the SI system, mass is measured in kilograms and force is measured in newtons. The terms are distinct, leaving little room for confusion. Looking at this split-screen comparison, the problem with the US customary system becomes obvious. Both mass and force share the exact same base name, the pound. Sharing that terminology causes the physical concepts of mass and force to blur and merge in a student's mind. Failing to separate a basic quantity of matter from a gravitational pull is a primary trap designed to catch unprepared test takers on the FE exam. Let's strip these definitions down. Pound mass, or lbm, is strictly a measure of a quantity of matter, how much physical stuff is in an object. Looking at this 1 lbm copper block, that quantity is an absolute constant. It does not change whether sitting on Earth, the Moon, or in deep space. Pound force, or lbf, measures weight. It is the specific push or pull exerted by gravity on that mass. While the mass remains locked, the force is a dependent variable. It scales directly with the strength of the local gravitational field. Swap these two separate physical properties in your calculations, and your dimensional analysis will collapse entirely. To see how quickly this collapse happens, we start with the standard baseline for calculating force, Newton's second law, F equals ma. Here is the standard equation loaded with US customary units. We plug in a 1 pound mass object accelerating at 32.174 feet per second squared. Multiplying these yields 32.174 pound mass feet per second squared. The output unit is not 1 pound force. The raw equation has failed. To fix this dimensional mismatch, the English engineering system requires a unique mathematical bridge to balance the units. Running standard physics equations without accounting for this quirk guarantees an incorrect answer on your exam. The fix is a specific gravitational constant, designated as G sub c. Looking at the NCEES handbook definition, the constant is exactly 32.174 pound mass feet per pound force second squared. This term is strictly a force unit conversion factor. Its entire job is to resolve expressions that makes mass and force expressed as pounds. Comparing these reveals a common error, confusing the conversion factor G sub c with local gravity. They serve completely different purposes. Gravity is an acceleration. The conversion factor is a static ratio. Therefore, Newton's second law becomes F equals ma divided by G sub c. This constant in the denominator is what enforces dimensional consistency. Without its inclusion, you cannot convert pound mass to pound force. This brings us to the Earth shortcut, the dangerous assumption that 1 pound mass naturally equals 1 pound force without running any math. Setting up the corrected formula, let's calculate the force on Earth using the new denominator. First, cancel pound mass. Next, feet cancel. Finally, seconds squared drop out. The unit left is exactly 1 pound force. On Earth, the magnitudes of mass and force are numerically equal. This specific numerical coincidence lulls engineers into a false sense of security, setting up the classic FE exam trap. Now shift to Planet X, an environment where local gravity is only 10 feet per second squared. Running the math with the correct conversion factor yields 0.31 pound force. Mass and weight are no longer a 1-to-1 ratio. The exam weaponizes non-standard gravity. If you assume 1 pound mass equals 1 pound force without dividing by G sub c, you will fail the question instantly. This conversion requirement extends far beyond basic kinematics. Looking at the NCEES handbook, the initial formula for potential energy explicitly builds the conversion factor into the denominator. It anchors the kinetic energy calculation as well. It is also integrated into fluid mechanics, driving fluid pressure and specific weight equations. Working engineers frequently omit this factor in their daily shorthand on the job, but in a testing environment, its use is mathematically required to produce a consistent set of units. Whenever a test question is presented in US customary units, your immediate instinct must be to check if the constant is required to balance the equation. Distinguishing between these two units impacts specialized engineering fields outside of standard mechanics. In engineering economics, calculations for raw material costs rely completely on pound mass. You are pricing the quantity of matter, not its weight. Looking at this electric motor shaft, electrical engineers see the distinction surface in rotating machines and the calculation of torque. Torque is typically expressed in pound-feet. You have to recognize this specific pound as a force, not a mass, to accurately convert the rating into Newton meters. Rigorous unit consistency dictates real-world mechanical and economic specifications. To survive the exam, remember, verify if a problem asks for matter or weight, apply the exact conversion factor, and never confuse GC with G. Mastering this distinction eliminates one of the most common unforced errors on the exam. Good luck!
Today we're going to carefully distinguish pound mass from pound force and learn how to use the conversion factor G sub C. We'll also solve 2 sample problems, then you'll try one yourself. In the US customary system, the word pound is used for both mass and force. That can be confusing, so we must distinguish pound mass, written as lbm, from pound force, written as lbf. Pound mass is a measure of how much matter you have. Pound force is a push or a pull. By definition, 1 pound force is the force that accelerates 1 pound mass at 32.174 feet per second squared. To keep the units consistent in US customary units, we introduce a conversion factor called G sub C. It equals 32.174 pound mass feet per pound force second squared. Newton's second law becomes force equals mass times acceleration divided by G sub C. Important, G sub C is not the same as G. The symbol G is the local acceleration of gravity, which has units of feet per second squared. G sub C is a conversion factor that keeps pound mass and pound force consistent. Sample problem 1. A mass of 10-pound mass is accelerated at 3 feet per second squared. Find the force in pounds force. We use force equals ma divided by G sub C. Plugging in values gives 10 times 3 divided by 32.174, which is about 0.933 pound force. Sample problem 2. A force of 20-pound force is applied to a 50-pound mass object. Find the acceleration. Rearranging gives it equals F times G sub C divided by M. So we get 20 times 32.174 divided by 50, which is about 12.87 feet per second squared. Now it's your turn. Try this one. A box has a mass of 150-pound mass. It is pulled with a force of 25-pound force. Find the acceleration. Pause the video and solve it. When you are ready, here's the answer. Let's recap. In US customary units, pound mass is not the same as pound force. Use G sub C to convert between them in Newton's second law. Remember the key idea. Force equals ma divided by G sub C when mass is in pound mass and force is in pound force.